All right, students, welcome to the next lesson for our data Year 12 unit. And it's going to be on a continuation of what you learnt last lesson on that rule called the 68, 95, 99.7 rule, or also the normal distribution rule. So if you haven't watched that lesson yet, I recommend that you do, because then this part will make a lot more sense if you watch the previous part. Okay, so let's get into this. So we're looking at standardized scores. Um, a standardized score, or also called a Z score, represents a data value by its number of standard deviations above or below the mean. So that's an important concept here. So a standardized score basically is a score that is represented in a way in terms of the standard deviations, okay, above or below the mean, which means above or below the middle. So if you think about standard deviations in the previous lesson with these bell curves, we learnt about how depending on how far somebody is from the mean, that's what a standard deviation is. So let's say everybody got around this score. If you got a standard deviation above, that means you got better, okay, than what most people got. If you got a standard deviation below, then that means you didn't do as well as the rest of the class. Okay, so it's kind of a fair way to measure people's scores as well. And also, the greater the standard deviation above or below, the further you are from the middle. So the higher the standard deviation, the better it is. And that's in terms of, SAC scores, but the lower the standard deviation, the worse it is. But I mean, it depends on the context. Like if you're, for example, if you're a runner and you measuring the time it takes for you to run a 100-meter race, right? Having a lower standard deviation is better because you want a slower time, okay? But having a higher standard deviation, if you're a runner, is probably not a good thing, because that means you're slower than the rest of the runners, okay? So it really depends on the context, but remember that a standard deviation is basically how far you are from the middle. Standardized scores can be used to fairly compare data values from different distributions. If the Z score, or if Z, is the standardized score, X is the actual score. So these are important variables that you need to know. X with a dash on top, we've learned about this, is the mean. O is the standard deviation, although in our calculators, remember that this is also SX. Okay, so just keep that in mind in the calculator. So this is the rule that we use to find your Z scores. It's going to be the actual value, take away the mean value, divided by the standard deviation, or just represented or in this short way here. So X, which is the actual score, take away the mean, divide that by the standard deviation. Okay, and we're going to use that formula. I'll just write it here again. So this is standard Z score. We're going to use this formula to do a couple different things. Okay, we'll use it to find the standard deviation. We'll use it to find the mean. We'll use it to find the actual score. And we can also use it, obviously, to find the Z score. So let's do it. I guess this is a graph that tells you from a raw score. So generally when it comes to Year 12, actually in Year 12, what they'll do is across Victoria, and this is how they kind of do your ATAR, I believe. So you get your raw score. So they add up all your raw scores, your study scores from all your subjects, and then they convert it into a standardized score. And then from there, okay, they are able to figure out where to rank people, what's the mean, and how far did people get from that mean. So you could say that someone who got like an ATAR of 99 could be like, I don't know, if the mean was like 60, and each standard deviation was 10, they got a standard deviation, or they have a standardized score of maybe, I don't know, like 6. Okay, because they're 6 standard deviations away from the middle, for example. Okay, so that's sort of how they do it, I believe. I'm not actually a professional when it comes to doing those ATARs, but that's what they do, I assume. Okay, let's get into some examples to make sense of this. So in a physics exam in 1 year, the mean score was 62%. So these numbers are going to be important. All right, I'm going to highlight and put symbols above what they mean. Okay, so this is just for physics. Okay, so the mean score was 62 and the standard deviation was 10. So this is the standard deviation, that symbol. In chemistry, so I'll use another color. In chem, okay, the mean score was 66%. Okay, I forgot to put a dash on top of this one. Okay, and the standard score or standard deviation was 5%. So that's the standardized score. Sorry, the standard deviation, not the standardized score. So Boris scored 82% on the exam and 78% in the chem exam. Calculate Boris's standardized score for each of his exams, and in which exam did Boris perform better in? Okay, so in this scenario, for the second part, actually I'll do the question and I'll explain the second part in a second. Let's do part 1. So we've got to calculate Boris's standardized score for both of the exams. All right, so remember the rule for finding your standardized score. It's Z is equal to your actual score minus the mean score divided by the standard deviation. So in this case, for Boris, his Z score, we'll do this for physics. Okay, we'll split it into 2, and this was for the other part is for chem. Alright, so for physics, his Z score would be Z is equal to, his actual physics score was 82%. So 82, take away a mean of 62. Okay, so 62 divided by the standardized score, or standard deviation, sorry, there of 10. Okay, so let's just solve this. 82 minus 62 divided by 10. So if I just do that off the top of my head, that would be 20 over 10, which means his standardized score is 2. So in comparison to the rest of the class, okay, he is 2 standard deviations, or his standardized score, sorry, is 2, which isn't too bad. Now let's do it for chem. So what we're looking for here is, I guess, which one would be higher. So if you look at these percentages, even though, actually, I'm going ahead again, so let me actually do it, and then we'll explain it. So for chem, his score, you can see there, was 78. All right, so 78. Oops. Take away the mean of, so for chem, it's a mean score of 66. So you've got to make sure you use the correct values. And the standard deviation was 5. Okay, this one's a bit harder to do off the top of my head, but let's calculate it real quick. So Z is equal to 14 over 5. So that means his Z score, let's use a calculator. So 14 divided by 5, Control Enter, is 2.8. So his Z score is 2.8. Now notice, so this is where the second part of this question comes into play now. So notice how in here, though his scores differ for, though one score, his physics score, was higher than his chemistry score, we could actually consider and say, okay, that he got better, okay, in terms of the standardized score, he actually got better in chem. And the reason why is because it's a higher Z score, okay, which means that he's 2.8 higher, or his standardized score is 2.8, which is greater than 2, okay, for physics, which means that he's higher up on the scale in chem as opposed to physics, even though, again, the scores, okay, were different. You could say that, oh, but sir, he got 82 in a physics exam, which means he got better than that in chemistry, which is only 87. But in comparison to the rest of the class, okay, although he got 82%, okay, it might mean, okay, and the standardized score is 2, it might mean that the rest of the class actually got really high as well. Whereas for chemistry, okay, he only got 78%, but a standardized score of 2.8. And what that means is maybe a lot of people scored lower than average. Okay, so that means that he actually got a better, higher standardized score for chem, because you could justify and say that a lot more kids scored lower. And you look at the mean as well, okay? The mean for both of them was slightly different. Okay, let's write that down. So you could say, what's the person's name? Boris. Boris did better in chem because his standardized score was higher. Compared to physics. Sorry for the horrible handwriting. Okay, let's go part B. Vladimir's standardized score. Okay, so let's do Vladimir this time. His standardized score in the physics exam was 1.35. So part 1 here is what percentage did Vladimir achieve in his physics exam? So again, if you remember, I mentioned that we actually use this score to find any value that we need, obviously within that formula. So in this case, we're looking for Vladimir's original score because it's given us the standardized score, it's given us the standard deviation, and it's given us the mean for physics. So we're looking for his original score. Let me copy and paste this because we're going to use this formula. All right, so if you look at Vladimir, you can see that he had a standardized score of 1.35. So his Z score was 1.35. We don't know what his score is. The mean for physics was, let's look at that, 62. Okay. And the standard deviation in physics was 10. Okay. Alright, so in this case, we're solving for whatever x is. Alright, so if you want, you can use your calculator for this, but you can also solve it by hand, which I will do. So we're trying to isolate x to find the score. So in this case, get rid of the 10, it becomes times 10. So you get 13.5 equals x minus 62. Here you've got a minus 62, so get rid of this, and it becomes 13.5 plus 62. So therefore x is equal to 75.5. So his original physics score is 75.5. Okay, part B. What percentage would Vladimir need to achieve to perform at least as well on the chem exam? So this is a bit tricky, okay? Because the way you need to interpret this question is that you might think, oh, doesn't he just need to achieve 75.5% to get as well? Well, remember, you want to get as well in terms of the standardized score. So you want his standardized score in chemistry to be the same as what it was in physics. As in, you want him to achieve just as well in terms of that, not in terms of the percentage, okay, but in terms of the standardized score. So the percentage is going to be different. Okay, so in that case, for part B, part 2, okay, we're going to look at our physics, the chemistry. So we want him to get a standardized score of 1.35 in chem, right? So for chem, it's going to be 1.35. Okay, and we're trying to figure out what score does he need to get in chem to get a standardized score of 1.35. So minus, actually, let me use blue for this one so guys aren't too confused. 1.35 equals x, take away. The mean score in chem was 66. Over, okay, and the standard deviation is 5, okay. So remember, in this case, what we're trying to find is what percentage score does he need to get so that he can have the same standard deviation, a standardized score as physics. All right, so let's calculate this. That's going to be tricky. So it's going to be 5 times 1.35, 6.75. Okay, so what I'm doing here again is I'm isolating the x. So that becomes times 5, which is 6.75 equals x minus 66. Isolate that x, there's a minus 66 there, it becomes plus 66. I'll just redraw it for you guys. So 6.75 plus 66 equals x. Therefore, x is equal to, adding that together, equals 72.75. So that means on chemistry, he needs to score at least 72.75 to get at least the same standard deviation, or in other words, at least the same or just as good of a score in physics. Okay, I hope that's made sense. Let's do a couple more examples to help you guys really understand this. So in a running race, the mean time is a 400-meter running race. The mean time is 60. Standard deviation is 4. So let me put those in. So mean time. Okay, the standard deviation is 4 seconds. In an 800-meter running race, the mean time is 140. Okay, so this is the mean. And the standard deviation is 9 seconds. And you competed 400 in a 400-meter race in 58 seconds and completed the 800-meter race in 144 seconds. Calculate and your standardized score for both races. Which did she perform better in? Okay. So let's do A. Part 1. A part 1, that's not confusing, I hope, but let's calculate the score for 400, and then for 400, and then for the 800 meter. Okay, so remember the rule for the standardized score was this: Z equals the mean, or your actual score, take away the mean score, divided by the standard deviation. Alright, so for 400, she got a race score of, her actual score was 58 seconds. And the mean time is 60 seconds. And the standard deviation for that is 4 seconds. So let's calculate that. Okay, so that's 58 minus 60, which is negative 2 over 4, which is a Z score of negative 0.5. Okay, easy. Let's do the 800 seconds. Okay, so in 800 seconds, she got 144 for her actual score, and for 800 seconds, the mean time is 140, and the deviation is 9. Okay, let's calculate that. So that will be 144 take away 140, which is 4 over 9. So as a actual Z score, I can't do that on my head, but let's use my calculator. 4 divided by 9 equals 4.9. 0.44. Z score of 0.44. Okay, now, in which race did she perform better in? All right, so remember, this is in the context of a race. So if it's a race, you want to make sure that you're faster than other people, right? So that means a negative Z score is actually better than a positive Z score. So for A part 2, okay, which did she perform better in? You would say that she performed better in the 400-meter race. Okay, because her Z score is actually below the standard, the median. Because okay, it was below. So did I say median? Below the mean. Yeah, and I should clarify that these are the races. Hopefully people don't get confused with the numbers. Okay, let's do B part 2. Natasha's standardized score in the 400 meter race was 2.1. How long did it take for Natasha to complete the 400 meter race? So we're trying to figure out her original time. Remember the Z-score, the Z-score rule here? So she got a Z-score of 2.1 there. So let's write that down. So 2.1 equals, and we're trying to find her original time, takeaway, and for the 400 meter race, remember the mean score is 60, so minus 60, and the standard deviation is 4. All right, so we're going to try and isolate x for this one. So here it's a 4 becomes times, so it's 8.4 equals x minus 60. Okay, and for now we go, this is a plus a minus 60, so it becomes plus 68 here. So 8.4 plus 60 equals x. So her actual time for the 400 meter race was 68.4 seconds. Okay, so that's for B part 1. So that was her original time. So in part 2, what time would Natasha need to achieve to perform at least as well in the 800 meter race? So you want to get it so that she can do, remember back to the previous question we did, we're trying to figure out, we want to make it so that she gets the same standardized score in the 800 meter race. Okay, so you want her to have a 2.1 for a standardized score in the 800 meter race. So using the formula, okay, so it's going to be 2.1 is equal to, we want to know what time does she need to get, this time in the 800 meter, so that she can get the same standardized score as she did in the previous 400 meter. So looking at the 800 meters, so the mean time is 140, so minus 140 over the standard deviation of 9. Okay, so we're trying to figure out what time does she need to get for her 800 meter race to get a standard deviation score, standardized score of 9. So isolate the x, this becomes times 9, so it'll be 18.9, sorry, my bad. Is x minus 140. Okay, isolate that x again, so that's minus 140, which becomes plus 140, so you get 18.9 plus 140 equals x. So that means for x, it's going to be 158.9 seconds. So that means for her to get a standardized score of 2.1 in 800 meter race, okay, she needs to get 158.9 seconds on her time. And that's basically it for these two examples and for chapter 1.11b. So go ahead and do the questions for this chapter. If you need any more help, let me know. I'm more than happy to try and explain this again. Otherwise, rewatch the video. Thanks, peeps.